In this diagram, you have 5 gates, exclusive OR and etc. And then you have 5 functions made of 3 bits. 2 to the third is 8. That means 3 bits can give you 8 functions, but we are using 5 of them. And when you have 2 inputs, A and B, coming into this circuit, all functions, all these gates will react. Okay, they will all give you values, outputs, but it depends on which function gate is active. Which of the 5 is a 1? The 1 decides the output from that gate is the output F. Let's go to 17. 17 is full adder. Remember, half adder only adds 2 bits and give you the sum. It doesn't give you the carry. And here, with full adder, it gives you the sum as well as the carry as the input for the next adder. This is saying if you have if you are adding two 3-bit numbers, for example, if you are adding 111 plus 101, that's 3 bits, then you need 3 full adders. If you add 4 bits numbers, you need 4 full adders. That's what this means. Here, this is discussing the LSB, the least significant bit, is a Cin. For this least significant bit, when you add 2 numbers, 2 binary numbers, there is no carry coming from nowhere, right? The rightmost bits should not have a carry coming in. But there is a carry coming in here. Why? Because this carry can perform besides one of these 3 functions. 1, it can perform incrementer A++, B++, add 1 to it. 2, it can perform chained arithmetic from a previous calculation. 3, it can perform subtraction. That means if this is 1, okay, the carry for the least significant bits, if it is 1, that means we are doing a subtraction. That's what this is saying. And so if that is a 1, okay, remember you do subtraction. How do you do that? You invert the bits, make it into a 2's complement number, and add it to the first operand. So if the incoming input is 1, and this X is a 1, 1, 1 exclusive OR is 0. If the incoming bit is 0, this is a 1, and this becomes a 1. So it inverts whatever this input is. That's the inverter. And then here, so this is the control bit, right? Just from the previous slide. Okay, if this is a 1, it will invert this bit. And then you add this 1 to it, then it becomes the 2's complement. That's how this works. So when this control bit is 1, it signifies it's a subtract because it will enable this exclusive OR gate to invert the bit and then add 1 to it to make it a 2's complement. And this diagram is showing you that with 3 bits, you can have 8 functions. So remember, 1 bit can have 2 values, 1 or 0. So with 3 bits, that's 2 to the third, that will give you 8 functions. So on this slide, this is multiplexer. Multiplexer accepts multiple inputs. Based on the control signal, it will select 1 input as the output unchanged. And this is saying this circuit, multiplexer circuit, is working like this. Based on the control signal, it will select A or B. If the control signal is 0, it will select A as the output here. If the control signal is 1, it will select B as the output here. That's what it is saying. So this is a multiplexer, 2-input multiplexer circuit. And you can trace it. You will find this truth table is correct. Let's look at this one, majority logic circuit. That means when all of them are true, the result will be true. When 2 of them are true, the result will be true. When 1 of them is true, the result will be false. Let's see if 1 of them is true. If A is true, is 1, this gate P will be 0, this will be 0, 0, and so you will have a false result. That's the majority logic circuit. And here, this one is the 3 of 4 detector. That means exactly when only 3 inputs are true, the result is true. Let's try 2 of them. If you have all of them as true, let's see, all of them are true, A, B, C, D, all ones, but D coming here is negated, it becomes a 0. So this AND gate gives you a 0. And so if they are all true, one of them at least is negated. So any of these AND gates will give you a false. Then you will have no true, your result will be false. But if you have 3 of them as true, then you are negating one of them. So, for this one you are negating D. This one is C, this one is B, this one is A. So you are negating one of them at least. If one of them is not true, it's negated and it becomes a true with this AND gate, and it comes out as a true. For example, let's do 1, 1, 0, 1. Okay, 1, 1, 0, 1. We are looking for the negation of that 0, which comes to this gate 2. So 1, 1, 0 negated to result in 1 and 1, and that gives you a 1. This is the sum of the AND gates, so this will give you a 1. But if you have all of them as ones, it will not work. This is the priority circuit. That means it will select the priority bit, the leftmost true bit, to be the result. So here you have x4, x3, x2, x1, x0 as 0, 0, 1, 1, 0, 1. The result should be 0, 0, 1, 0, 0 because we are choosing the leftmost true bit as the result. Okay, so that should be the result. Let's see how this works. x4 is 0. Coming in, y4 is 0. y4 is 0. And 0 coming, negated becomes a 1. But x3 is a 0. So y3, the result is 0. y3 is 0, negated, it becomes a 1 coming to gate 3. And this, remember, is a 0, negated becoming a 1 coming to gate 3. So we have 2 1s now. And x2 is a 1. So this gate 3 yields a 1, which is y2. This is a 1. And then this 1 coming here, it becomes a 0. So this gate 2 will give you a 0. And that is a 0. A 0 negated becomes a 1, but your x0 is a 0. So this gate 1 gives you a 0. y0 is a 0.